Hello everyone, this is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. So in this session, I'm going to explain about ideal as well as practical differentiators of operational amplifier. So while coming to the contents, just I'll revise what is meant by operational amplifier and what are the different applications of the operational amplifier, and in that one of the application is the differentiator and also the practical differentiator. In order to overcome the problems of ideal differentiator, we are moving for the practical differentiator. So before going to the applications, first of all, I wanted to revise once about the operational amplifier here. I have already mentioned in the previous session also the specialty of the operational amplifier is along with the amplification, it can able to perform all the mathematical operations, and it can able to provide very high amount of gain compared to the normal single stage or multi-stage or differential amplifiers. So this operational amplifier nowadays available in the form of ICs. The name of operational amplifier IC is 741. So why it is named as 741 means total 7 functional pins are available here. So among that, 4 are utilizing for the inputs and 1 for the measuring the output signal. So it can able to amplify both the AC as well as DC signals, and it can able to amplify all the range of frequency signals from 0 to some megahertz range. And in the internal circuit of operational amplifier, we are going to utilize the different configurations of the differential amplifier. The differential amplifiers are available in 4 configurations, that is dual in, balanced output differential amplifier, dual input, unbalanced output differential amplifier, single input balanced output differential amplifier, and single input unbalanced output differential amplifier. So among all these 4 configurations, some of the configurations we are going to utilize in the designing of the operational amplifier. So what are the features which are present in the differential amplifier are also applicable for the operational amplifier. That is, it can able to amplify the differential voltage whatever we are applying for the 2 inputs of the differential amplifier, and it can able to provide very high common mode rejection ratio. That is nothing but when we are providing the common input signal, that can improve the CMRR value here. So these effects are also applicable in the case of operational amplifier because of having internal stages all are differential amplifiers. So in the case of our differential amplifier, how we can able to differentiate these 4 configurations here means depends upon how many number of inputs we are providing for the amplifier, and output how we are measuring here. We are measuring at a common point of 2 collectors, or else we are measuring at a single collector terminal of the amplifier. So depends upon that we can able to differentiate these 4 configurations of the differential amplifier. And while operating the operational amplifier for any application, it should first of all it should maintain the differential voltage value as 0, and also to make this value as 0 we can make some modifications in the circuit but within the limits. So this is the main requirement in the case of operational amplifier to run for any particular application. Why? Because if this value is something is present means there is a variation in the output signal here. So that's why in order to overcome that, we have to maintain always this value as 0. We have to try to make this value as 0 in the practical cases. So now we will see the different applications of the operational amplifier. So the first application is the linear application. So what is meant by this linear application? In the case of linear applications, the output voltage or output current varies with respect to the applied input voltage, so that we can say that particular circuit is the linear circuit. So to design this linear circuit, we can utilize this operational amplifier. And What are the different linear applications are there? So in the case of linear applications, we are going to utilize the negative feedback, not the positive feedback. That is nothing but the output of the operational amplifier. Again, we are connecting back to the inverting terminal of the operational amplifier, so that we can say it as it is in the negative feedback form. So why only we are preferring the negative feedback? Why not we are preferring the positive feedback here means that is depends upon the application, which type of application we are going to design. Depends upon that we will utilize the different types of positive or negative feedback. But in most of the cases we'll prefer the negative feedback. Why? Because negative feedback can able to provide more advantages compared to the positive feedback. That is nothing but those negative feedback circuits can able to reduce the noise effects and distortion effects and any variations of the components, and those can able to stabilize the system, and those can able to improve the bandwidth of the system. So because of all the reasons, most of the cases will prefer the negative feedback for the amplifier circuit. And the examples for this linear applications are voltage follower, adder or subtractor, integrator and differentiator. All are comes under the linear applications of the operational amplifier. And second category of the applications are non-linear applications. So in the case of non-linear application, in this case we are providing the feedback from the output to the non-inverting terminal of the operational amplifier. That is nothing but we are utilizing the positive feedback instead of negative feedback. So the use of this positive feedback is to generate the waveforms. That is for oscillations purpose we can utilize this. So in this case, the feedback may be provided to the inverting input terminal also through the non-linear elements like diodes or transistors. In the diodes as well as in the transistor, there is no variation of the output voltage linearly with respect to time. Always it may vary in non-linearly. So that's why those are the non-linear elements or non-linear components. So examples for this non-linear applications are precision rectifier to perform the rectification and to perform the log operation, log amplifier and anti-log amplifiers, and to compare the signals and to generate the square wave signal by using the schematic trigger circuit. So these all are the non-linear applications of the operational amplifier. So along with this, we can also utilize the IC741, that is operational amplifier, as an amplifier, oscillator to generate the waveforms, and timer to create the waveforms, and counter to generate the timing waveform required for the processors, and to design the computer memory, and to design microprocessor as well as microcontroller chips. We can able to utilize these ICs. And whenever we wanted to utilize the operational amplifier for any particular application, so that particular amplifier should obey the two rules. Those are the inputs to the op amp draw or source no current. That is nothing but once we are designing the circuits without providing any input signal, it should not draw or source any particular source current from the circuit. That is the first condition here or first rule. And while coming to the second rule, to maintain the differential voltage as zero, always we have to maintain the two input voltages V1 as well as V2 must be zero. And to make it as zero, this differential voltage as zero, that is nothing but Vd equal to V1 minus V2. We have to we may make some variations or changes in the circuit here. So, but these two rules are very important to design any practical application of the operational amplifier. So now we'll see the first linear application of the operational amplifier, that is differentiator. So we already know that what is meant by differentiator. So the function of the differentiator is to, it will differentiate the applied input signal. Okay, so that's why we can call it as the differentiator. The particular circuit here, we can say it may be the operational amplifier differentiator or maybe the normal differentiator, but the function is same here. It should perform the differentiation operation. Suppose if we are designing the differentiator circuit by utilizing the operational amplifier, so that we can call it as the active op-amp differentiator or active differentiator. So now we will see the ideal active op-amp differentiator. So before going to that, generally by using RC elements also we can able to design the differentiator. That is nothing but one capacitor and one resistor combination. If we take and we are providing some particular voltage to this, we will get across the output as a differentiation of the applied input signal. So the same thing we can able to design by using the operational amplifier. So why we are moving for the op-amp differentiator, even though we are having with the RC elements, means we can able to improve the performance of the differentiator, and we can able to improve the gain of the system, and we can able to reduce the noise effects of the system by using the feedback in the operational amplifier. So because of all that reasons, we can able to go for the ideal active op-amp differentiator. So the circuit of this that one is I'm showing here. So this is the op-amp symbol with the two input terminals, inverting terminal as well as non-inverting terminal, with the two supplies plus VCC and minus VCC, and the output voltage. So this is the normal op-amp, minus plus V0. This is V2 and VB. So for this operational amplifier, we are adding some external components to make it as the differentiator. So what are the external components we are adding here? Means one resistor and one capacitor. So the capacitor we are connecting across the inverting terminal of the operational amplifier. So here we are connecting the capacitor. And to provide the feedback from output to the inverting terminal, we are utilizing the feedback resistance RF. So that's why the output signal through the feedback resistance we are connecting back to the inverting terminal. So we can call it as the inverting differentiator. Why? Because we are providing the input directly to the inverting terminal. In the previous session, we have discussed what is the inverting operational amplifier and what is non-inverting operational amplifier. In the case of inverting operational amplifier, we are providing the input to the inverting terminal and the non-inverting terminal should be grounded. And in the case of non-inverting operational amplifier, we need to provide the input for the positive terminal and the inverting terminal should be grounded. So in this case, we are providing to the inverting terminal. So the basic function of this one is to provide the differentiation of the whatever the input signal we are providing here. So V0 equal to differentiation of Vn we will get here. So how it is providing that from the analysis we'll see now. So for that I am considering the same circuit again here, and here the positive terminal or non-inverting terminal is grounded. That is nothing but VB, the voltage at B point is 0 here. And according to the virtual ground concept, once this VB value is 0 or it is grounded, means at this point voltage VA must be 0. About the virtual ground concept we discussed in the previous session. In the case of virtual ground concept, always the differential voltage must be 0. So to make it as this differential voltage must be 0, what is the voltage which is present in one particular terminal is same will appear in the another terminal of the operational amplifier. That may be the 0 or some particular value, or that may be the ground. So what is the value is there here, the same thing will appear here. So that's why virtually it is appearing in this terminal also. So that's why this concept we are calling it as the virtual ground concept. So in this case, both the VA voltage as well as VB voltage across both the inverting as well as non-inverting terminal voltages are 0. Okay. And So though this particular VA voltage is 0, means there is no flow of current inside the operational amplifier. See, inside the operational amplifier, there is no current is flowing here due to the virtual effect or virtual ground effect. So the entire current or I1 current which is flowing through this capacitor and through this RF resistance to the output. So that's why to find this I1 current from the input side, I'm writing I1 equal to, here we have C1 into differentiation of V in minus VA, differentiation of V in minus VA by dt here. So here value of VA is equal to 0. So that's why this equation will become I1 equal to C1 dVn by dt. So this one we are taking it as the first equation. So this is the current which is flowing from here to here only, that is V into VA only. So in order to find the current which is flowing in the VA to V0. So for that, again I am writing the equation from the output side. The same circuit again I am considering here to write the next equation, that is from the output side. It is nothing but in this particular loop, how much current which is flowing. To find that, we are writing that current as I equal to this voltage VA minus V0 divided by RF resistance. So the value of VA is 0 due to the virtual ground concept. So this one will become minus V0 by RF. So this is the second equation. So to find the final equation or final output voltage, we have to equate the two equations, that is 1 and 2 equations. So from the 1, we got it as C1 dVn by dt. So from the first equation, C1 dVn by dt, and from the second equation, the value is minus V0 by RF. The two we are equating here. So after simplification, we will get V0 equal to minus C1 RF times differentiation of the input voltage. So here what is mean by RF C1? RF C1 is nothing but the time constant of the circuit or time constant of the differentiation. So from this equation, we can say the output is RF C1 times the differentiation of the applied input signal here, and this the different how much amount of differentiation it is providing is depends upon the values of C1 and RF here. So and again the negative sign in the output indicating that the output is 180 degrees phase shift with the applied input signal. Why we are getting like that means we are providing the input to the inverting terminal here. I have already mentioned when you are providing the input to the inverting terminal means always in the output you will get the 180 degrees phase shift. So that's why in the output voltage we are getting the negative side. So this is the output voltage in the case of ideal op-amp differentiator. So now this particular circuit, we will apply different voltage waveforms, and what is the output we are going to get, we'll see now. And the main advantage of this op-amp differentiator is the time constant required for this is very, very less. So while coming to the input as well as output waveforms for this circuit, the first input waveform I am taking here it as step input. So how we can draw the step input? We already know step input is this straight line with the magnitude A or something. This is my Vin of t. It is varying with respect to t. So how I can represent this signal here? Vin of t is equal to A, the magnitude A for t is greater than or equal to 0. Okay, so this is the particular step input signal I am going to apply for the op-amp circuit. And what is the output I am going to get? Here it is. We can calculate from the output equation, that is V naught of t is equal to minus RF C1 d by dt of V naught of t. So for simplicity, as it is the ideal differentiator, I am taking my time constant value as unity, that is 1. And what is my input voltage? A. So I am going to substitute these two values in the equation 1. So my V naught of t is equal to minus 1 into d by dt of A. So the differentiation of A is nothing but 0. That is constant. The constant value is 0. So V naught of t, we are getting here it as 0. So what is my output waveform here? That is also with respect to t. V naught of t, we will get the spike, and after that total it is 0 here. So why we are getting the spike and it is 0 here means, in the case of differentiator circuit or anything, the step input takes some finite time to reach from 0 to A. So that's why in the output also it is not directly going to 0 here. So that's why it is slowly, it is decreasing towards 0, and after that it is making it as 0. So because of that reason, we are getting here it as some spike or impulse. So when you apply the step input to the differentiator circuit, the output we will getting here it as the spike. Okay, output we will getting here it as the spikes here. So this is when we apply the step input to the differentiator, we will get it as the spikes here. And we are getting the step signal as the positive signal with the magnitude A. But why we are getting here it as the negative spike means, in the differentiator, it is the inverting differentiator, and in the output voltage negative sign is there. So because of that reason, it is in the negative direction it is coming. And the next input, I am going to take here it as square wave input. So when we apply the square wave, so how we can design the square wave? Here it is. This is my Vn of t with respect to time t. So this square wave we can able to implement by using the train of step signals. If we combine the positive step signal as well as negative step signal, we can able to create the square wave signal. That is nothing but, this is the positive step and this is the negative step. And again positive step and negative step. 0, t by 2 and t signals here. So here the magnitude is A I am taking, and here I am taking it as minus A. So my input signal Vn of t is equal to A for the duration is 0 to t by 2 range, and after that my Vn of t is equal to minus A within the duration from t by 2 to t. Okay. So this is the input signal we are providing. And what is the output signal I am going to get for this particular input signal? So for that purpose, I am taking my output voltage V naught of t equal to minus RF C1 d by dt of V naught of t. So though it is the ideal differentiator, I am taking the time constant value as 1. And the input voltage is A and minus A here. So that is nothing but, in this case, what we are going to get means, for the positive square signal, we will get it as the negative spike. And for the negative square signal, we are going to get the positive spike here. So V naught of t is equal to minus 1 into differentiation of A, and also minus of minus 1 into differentiation of minus a we are going to apply here. That is nothing but within the 0 to t by 2 duration it is a, and from t by 2 to t duration it is minus a. If we substitute the two values, differentiation of constant is 0. So that's why value we are getting to 0 in the case of positive as well as negative side. That is nothing but in the output signal, that is also with respect to time, it is varying v naught of t equal to, for the positive square signal we will get it as negative spike, and again it is going to 0, and for the negative half cycle we will be getting here it as positive spike, and again it will move to 0. So this one will repeat for all the cycles. So if you apply the square input to the differentiator circuit, we will get it as train of spikes or impulses as the output in the case of differentiator circuit or in the ideal differentiator circuit. And the next input I am going to take here it is sinusoidal signal. Sinusoidal waveform or sinusoidal input. So this sinusoidal signal I am taking here it as, this is 0, this is t by 4, this is t by 2, and this is t here, and the maximum amplitude is Vm and the minimum negative amplitude is minus V. Okay, so my input signal here it is Vm sine omega t, range from 0 to t range. So for this input signal, and what is the output signal I'm going to get here? That is from the output equation I can write V naught equal to minus Rf C1 d by dt of V naught t. So this one take it as 1. Now substitute the value of Rf C1 as well as V naught t here. So my Rf C1 value is 1 here. Okay, and V naught t is Vm sine omega t. So V naught equal to minus 1 into d by dt of Vm sine omega t. So V naught equal to minus Vm into cos omega t into omega. So this is the output voltage. So now we will check it for different time periods or timing signals here. So at t equal to 0, what is my output voltage? At t equal to 0, cos 0 is value, cos 0 value is 1. So that's why it is minus Vm into omega we will get. And at t equal to t by 4, my V naught value is 0. Why? Because this cos t by 4 value is 0 here. And at t equal to t by 2, my V naught of t value is plus Vm by Vm into omega we will get here. So now we will draw the output sequence. That is also varying with respect to time. V naught of t, that is nothing but t equal to 0, that is minus Vm omega value we are getting. So it is starting at minus Vm till t by 4. Okay. And at t by 4 this value is 0. And at t by 2 it is moving to the maximum value. So it will come or it will repeat for all the cycles minus Vm. So that is nothing but, in the case of differentiator, when you provide the sinusoidal signal, we will get the output as the cosinusoidal signal. So these three are the different input signals and their corresponding output signals when we apply for the ideal differentiator circuit. So now we will see the frequency response of this ideal differentiator circuit. So to see the frequency response of this one, I am going to consider the output voltage or output signal, how much we are getting from the ideal differentiator circuit. That is V naught of t equal to minus RF C1 into d by dt of V naught t. Okay, to find the frequency response, I am applying Laplace transform on both sides. So that we will get it as V naught of S is equal to minus RF C1 S into V naught S. And next, to get the frequency response again, I wanted to replace S with J omega. So when we replace S with J omega in the second equation, we will get it as V naught of J omega is equal to minus RF C1 J omega into V naught J omega. So from this, if we write the gain, that is the ratio of output voltage by input voltage, V naught of J omega by V naught of J omega by V naught of J omega, and that value is minus RF C1 J omega. And to get the frequency response, again we need to find the magnitude of this gain. So to find the magnitude of this gain, A equal to V naught of J omega, V naught of J omega, determinant, we will get it as J omega RF C1 value, where omega is equal to 2 pi f here. So that I can write it as J 2 pi f RF C1 is the magnitude of this ideal differentiator. Magnitude of this ideal differentiator circuit. And so the frequency response or the gain of this particular ideal differentiator circuit is depends upon the which frequency signal we are providing here. Suppose if our f value is 0 means obviously our gain value is also 0 here. As frequency is increasing means obviously the gain value is also increasing here. Okay, so that we can observe here. Suppose I am taking my gain equation, that is 2 pi f RF C1 value. Okay, so I can also write it as I am considering one F1 value, that is cutoff frequency value. If we consider this Fn value, I can write my magnitude value as F by F1, where F1 is the cutoff frequency and that value is 1 by 2 pi RF C1 value. So if we consider this, we will get the magnitude as this much. And here, if our applied input signal frequency is less than this cutoff frequency F1, in that case, we will get the value of gain is negative. And suppose our applied input signal value is equal to this cutoff frequency range, in that case, we will get the gain value as 0. We are writing from this magnitude equation only. Or else if your applied input signal is greater than this cutoff frequency, we will get it as the positive value of the gain. So this and all we can observe in this frequency response of the ideal differentiator. So if you see here, at frequency equal to 0, at frequency is equal to 0, if frequency is less than F1, here is our F1 value we are taking here. If your applied input signal frequency is less than this F1 means we are getting the negative gain, minus 20 dB. And if F is at F1, we are getting the gain value as 0 here. And if your applied input signal is greater than F1 means it is increasing here. Always at 20 dB per decade gain value is increasing here. So this is the frequency response of the ideal differentiator circuit. Okay. So this ideal differentiator, it is performing the differentiation operation and it is providing the output for various input signals. That is well and good. But this ideal differentiator is facing with some problems. That is nothing but when you increase the frequency at high extent, that is nothing but at high frequencies, the differentiator is going to unstable and the signal is breaking into oscillations. And after some time, the differentiator may go into the saturation region. So once it is entered into the saturation region means it will not provide any gain and it will not provide any output signal. So that is the one drawback. It is facing at high frequency range of the signals. It is unstable and it is going into the unstable condition. And along with that, at high frequencies, the reactance of the capacitor is decreasing here. So once the reactance of this capacitor C1 is decreasing means there is a effect of noise problem in the ideal differentiator. So in order to overcome these two problems, instability as well as saturation problem as well as noise problem, we are moving for the practical differentiator. So how we can able to make this practical differentiator? So when we add extra elements, one resistance as well as one capacitor to the ideal differentiator circuit, we can able to make the practical differentiator circuit. See, this circuit is the ideal differentiator circuit. So for this ideal differentiator circuit, we are adding the extra element R1 in series with the C1 capacitance and CF in parallel with the RF resistance. And along with that, we are also adding the R compensation. So this R compensation is used for the bias compensation here. So that is used to nullify any stabilization effects in the practical differentiator circuit. So in order to find the output voltage of this practical differentiator, again we have to find the different currents which are flowing in the circuit. So before going to that, this positive terminal or non-inverted terminal is grounded here. That is nothing but the voltage at point B is 0. And due to the virtual ground concept, the voltage at VA is also 0 here. Okay, voltage at VA is also is 0 here. So once this VA is 0 and VB is 0, so the current which is flowing in the R1 C1 is flowing into the RF resistance as well as in the CF capacitor, and it is not flowing in the op amp here. So the total current I is sum of I1 plus I2 which are flowing in the RF and CF capacitors here. Okay, so here to find the current here, what I am taking the current I. From the input side, to find the current I am writing V in minus VA divided by Z I am taking, where Z is nothing but the series combination of R plus C1. So R plus C1 means how we can write here it as Z equal to R plus 1 by SC1 I am writing. I am directly taking in the Laplace transform form. So I equal to V in minus VA by R plus 1 by SC1 here. So here VA value is 0. So I can write my I value as V in into SC1 by 1 plus R into SC1. So this is the first equation. And similarly, we need to find the I1 as well as I2 currents. so that we can calculate from the output side. So to find the I1 current, okay, to find the I1 current, that is VA minus V0 divided by RF resistance. So here VA value is 0. So that's why I1 is equal to minus V0 by RF. So this one I am taking it as my second equation. And next, to find the second current, that is I2 is equal to VA minus V0. VA minus V0. That is nothing but we can write it as CF into differentiation of VA minus V0 by dt. So here VA value is equal to 0. So we will get it as minus CF differentiation of V0 by dt. So if we write in Laplace transform form, we will get it as minus SCF V0 of S. So, this is the third equation, I2. Okay. So now apply KCL at node A. If we apply the KCL at node A, we will get it as I equal to I1 plus I2. So what is the value of I we got here? I value we will get it as S C1 V in by 1 plus R R1 C1 into S here. Okay, 1 plus R1 C1 into S is equal to I1 current is minus V0 of S divided by RF plus minus SCF V0 of S here. Okay, so SC1 V0 of S by 1 plus R1 C1S is equal to, if you take V0 of S common here, we will get it as 1 by RF plus SCF. So I can write it as SC1 V0 of S by 1 plus R1 C1S is equal to minus V0 of S into 1 plus RF S into CF by R. So from this, if we write V0 of S by V0 of S, we will get it as minus S RF C1 divided by 1 plus R1 C1S into 1 plus RF CF into S. Suppose if I am taking R1 C1 is equal to RF CF. So in this case, this equation will become V0 of S by V0 of S is equal to minus S RF C1 by 1 plus S into R1 C1 whole square. And also, if I am making RF, it is RF. RF C1 value is far greater than this R1 C1 as well as RF CF. So in that case, we can able to reduce this expression as minus S into RF CF. The gain equation will become minus S into RF C1 here. Okay, and so the output voltage V0 of t is equal to, if we apply the inverse Laplace transform, we will get it as RF C1 minus RF C1 times the differentiation of the input voltage. So this is the final practical differentiator output voltage. And always the RFC1 value here. This RFC1 value is always we have to maintain very less compared to the time period of the applied input signal. Then only we can able to get the true differentiation or proper differentiation from the circuit. And next, to find the frequency response of this practical differentiator circuit. So to find the frequency response of this practical differentiator circuit, we have to find the gain of the practical differentiator circuit in terms of frequency. So from the ideal differentiator equation only, we are going to find the practical differentiator gain. So from the ideal differentiator, the gain equation is minus SRFC1 by 1 plus SR1C1 square here. Sorry, this is the practical. We are discussing about the practical differentiator circuit. So here we are replacing S with J omega in both the cases, so that we will get it as V naught of J omega divided by V naught of J omega, that is minus J omega RFC1 times divided by 1 plus J omega R1C1 whole square, and where omega is equal to 2 pi f here. So if you substitute that, we will get this. It is the square here, not 2. And now I am taking two cutoff frequencies, FP as well as FA here, 1 by 2 pi R1C1 and 1 by 2 pi RFC1. Why? Because we are having two time constants here. So if we replace these FA, FP in this equation, we will get it as minus J into F by FA divided by 1 plus J F by FP whole square. So the two frequencies FA and FP are called the two break frequencies in the practical differentiator. So now we'll see the frequency response from the graph here. So the gain value we got this much here, and in this case the RFC1 time constant is very large compared to the R1C1. So that's why the first cutoff frequency is less than the second cutoff frequency. So because of this reason, as frequency increases, the gain increases till F equal to FB here. Okay, F equal to FB, the gain will increase here till FB means this F2 here. I am taking it as FB and this as FA. So till F equal to FB, the gain is increasing plus 20 dB per decade here. And whenever our applied input signal frequency is reached to FB, the gain decreases at a rate of 20 dB per decade. After that, it is decreasing here. So this 40 dB per decade change at F equal to FB occurs due to the combination of both the time constants R1C1 as well as RFC1. So for RFC1 is less than T means we will get the proper differentiation. I have already mentioned this point. So also the combination of both the time constants R1C1 as well as RFC1 helps to reduce the noise effects as well as offset effects in the case of practical differentiator. So that's why always we have to choose proper values of all the resistances as well as capacitances to design this practical differentiator circuit. So the same one I am showing here. So till F1 it is actually at 0, it is 0 dB, and at first corner frequency it is reaching to 0 dB here, and between first to second corner frequencies it is increases to plus 20 dB per decade, and after second corner frequency it is decreasing to minus 20 dB per decade here. So in this session, all the waveforms I have taken from the electronics hub, all the circuits as well as waveforms I have taken from the electronics hub. And so till now we have discussed about the ideal as well as the practical differentiators, and next we will see how to design the practical differentiator circuit. So to design the practical differentiator circuit, we require two cutoff frequencies FA and FP. So in that, first of all, we have to choose the first cutoff frequency, and that first cutoff frequency is the highest input amplitude of the signal. or highest frequency of the input signal. And always we have to choose C1 value must be less than 1 microfarad, and from that we can able to find the RF value. And FB value should be 10 times greater than the FA. Why? Because always FA should be less than FB to get the proper differentiation. And finally calculate the values of R1 C1 from this particular relation. And R compensation resistance also required here. Generally that is the parallel combination of the R1 and RF. But in the practical case almost we will take it is equivalent to R1 here. Why? Because R1 resistance is very less compared to the RF resistance. So that's why we are making it as R1. Why? Because these two are in the parallel combination. Whenever two resistances are in the parallel combination means we will get always the small value as the result. So now we'll see one example related to this before going to that, where we can utilize this practical differentiator. Generally to design any wave shaping circuits. In that, to detect any high frequency components in the input signal, we will utilize this. And also in the FM demodulators, in order to see the rate of change of the detector, to see that we will utilize this practical differentiator circuit. So now we'll see one problem related to this practical differentiator, that is design a practical differentiator circuit that will differentiate an input signal with F maximum of 150 Hz. So I have already mentioned F maximum is nothing but our first cutoff frequency FA. So that's why in the first step I am taking FA equal to F maximum is equal to 150 Hz. And I'm choosing the capacitance value C1 equal to 1 microfarad. So here we require R1 C1 value as well as RF CF value so that we can able to design this. So here we have choose C1 as 1 microfarad. So FA equal to 1 by 2 pi RF C1. So we know the value of FA as well as C1 value here and the frequency value here. So after substituting all that values, we will get the RF value. So now we have RF and C1 value and FA value. So now the third step is FP. We need to calculate the second cutoff frequency FP, that is 10 times the FA value. So if we substitute that again, we will get the FP value also. And from the FP again we can calculate the R1 value. So now we got all the values here. This is C1 and this is FA value and this is RF value and this is FP value and R1 value. So by using all these values, we can able to design the differentiator circuit. So the practical differentiator here, it is minus plus the resistance R1 C1 here. This is R1 C1. This is input signal and this is the R compensation resistance and the feedback. In the feedback we are having the capacitor as well as the resistance CF and RF. So this is our practical differentiator circuit. So to put the values on this particular circuit, I'm going for the relation R1 C1 equal to RF CF. So from this we will get the value of CF also. And R compensation is a parallel combination of the R1 resistance and RF resistance. So that we will get it as 96.44 ohms. So generally actually this R compensation value is almost equal to the R1 value. So now substitute all these values. R1 value we got it as 106.11 ohm and C1 value we got it as 1 microfarad and RF value is 1.06 kilo ohms and CF value is 0.1 microfarads and R compensation value is 96.44 ohms. So in this way we can able to design any kind of practical differentiator by using the frequency, the given frequency. Once again, I am repeating the steps. First, we need to choose the first corner frequency, FA, that is the maximum given frequency. And next, we have to choose the C1 capacitance, 1 microfarad. And when we know the FA and C1 values, we can able to find the RF value. And next, in the third step, we have to choose the second corner frequency, FB, that is 10 times the first corner frequency, so that we will get the second corner frequency also. So from that second corner frequency, we can able to find the R1 resistance. And from this relation R1 C1 is equal to RF CF, we can able to find the feedback capacitance value and also the R compensation resistance. So after finding all the resistances as well as capacitances values, we have to draw this practical differentiator circuit and we have to indicate whatever the values we have already calculated from the given problem. So in this session now, we have discussed different applications of the operational amplifier. In that, we went for the ideal differentiator, and in order to overcome the problems of that ideal differentiator, we also discussed the practical differentiator. And we have seen the frequency response of ideal as well as practical differentiators. And we also seen the design procedure for the practical differentiator and also the problem related to the designing of practical differentiator. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.